Hello friends, today we'll discuss the separation of variables. We know that the separation of variables technique for the solution in separating the partial differential equations of n number of variables into n ordinary differential equations, and each separation introduces an arbitrary constant of separations. Suppose if we have n variables, then we have to introduce n minus 1 constants determined by the conditions imposed in the problem being solved. And to solve some partial differential equation by using the separation of variable methods, just one problem we have here to solve. The use of separation of variables. By using the use of separation of variables to solve two-dimensional Laplace's equation in Cartesian coordinates, del square psi is equal to 0, where del square is the Laplacian operator and is given by in three-dimensional coordinate system is del square is equal to dabba square by dabba x square plus dabba square by dabba y square plus dabba square by dabba z square. But here to solve two-dimensional Laplace's equations in Cartesian coordinates, and therefore dabba square psi by dabba x square plus dabba square psi by dabba y square is equal to 0. Here is the equation number 1. Let us assume that the solution of equation 1 is in the form of psi of xy equal to x of x, y of y, divided by 2, where x of x is function of x only and y of y is function of y only. And therefore let us try to split the partial differential equations 1 into two ordinary differential equations, and therefore differential equation 2 with respect to x twicely we get, that is dabba psi by dabba x equal to, y is the constant, say y constant, dabba x by dabba x is the first order derivative. Again differentiate these equations with respect to x, therefore dabba square psi by dabba x square is equal to y dabba square x by dabba x square. Similarly, differentiate equation 2 with respect to y twicely we get dabba psi by dabba y is equal to x dabba y by dabba y, and therefore dabba square psi by dabba y square is equal to x dabba square y by dabba y square. And substituting these values in equation 1, we get y dabba square x by dabba x square plus x dabba square y by dabba y square equal to 0, divided by 3. Dividing throughout by xy, we get इक्वेशन 3 ला xy ने डिवाइड केलं आणि म्हणून मग आपण therefore 1 upon x dabba square x by dabba x square plus 1 upon y dabba square y by dabba y square equal to 0. Or this equation can be written is in the ordinary differential equations because of the x depends only on x, y depends only on y, only one independent variables, and therefore 1 upon x d square x by dx square equal to minus 1 upon y d square y by dy square divided by 4. आणि म्हणून मग therefore LHS of equation 4 depends only on x while RHS depends only on y. And this equation is true only when each side is equated to some constant known as constant of separation, and let the constant of separation is say minus lambda square, and thus we get the two solutions of equation 4. 1 upon x d square x by dx square equal to minus lambda square. Therefore, d square x by dx square equal to minus lambda square x, or d square by dx square plus lambda square x equal to 0. मग त्या ठिकाणी ऑर्डिनरी डिफरन्शियल इक्वेशन तयार झालं ते we had to obtain solutions by using d by dx is equal to capital D, आणि मग ह्या ठिकाणी d square x प्लस लॅम्बडा स्क्वेअर एक्स असं होईल बरोबर 0. म्हणजेच d square is equal to minus lambda square, and therefore d is equal to plus minus I lambda, and hence its solution is given by, that is, x is equal to a cos lambda x plus b sin lambda x. These are the solution of these equations. Similarly, next term, minus 1 upon y d square y by dy square is equal to minus lambda square. And therefore, minus d square y by dy square is equal to minus lambda square y. Both sides negative, then it should becomes positive. And therefore, d square y by dy square equal to lambda square y, and hence d square y by dy square minus lambda square y is equal to 0. Then equation B. Therefore, so its solution is given by, again, d by dy is equal to capital D, and therefore d square y minus lambda square y is equal to 0, and therefore d square minus lambda square is equal to 0, and d square is equal to lambda square, and therefore d is equal to plus minus lambda, and hence its solution is given by y is equal to c e raised to lambda y plus d e raised to minus lambda y due to the b, and thus the general solution of differential equation 1 is given by psi of xy is equal to x of x आणि y of y. मग ह्या ठिकाणी तुम्हाला x of x हे इक्वेशन ए मिळालेलं आहे, आणि y of y हे इक्वेशन बी दिलेलं आपण नाव त्याला, आणि therefore psi of xy is equal to a cos lambda x plus b sin lambda x into another bracket c e raised to lambda y plus d e raised to minus lambda y. These are the separation of variables of two-dimensional Laplace equations. Next problem. Solve separation of variables in the Helmholtz equation in Cartesian coordinate system. The Helmholtz equation is given by del square psi plus k square psi is equal to 0. But del square is the Laplacian operator and is given by del square is equal to dabba square by dabba x square plus dabba square by dabba y square plus dabba square by dabba z square, and hence in 3 dimensions the Helmholtz equation becomes dabba square psi by dabba x square plus dabba square psi by dabba y square plus dabba square psi by dabba z square plus k square psi is equal to 0 due to the equation number 1. And so the solution of equation 1 is in the form of psi of x comma y comma z is equal to x of x, y of y, z of z. You know the two, where x of x is function of x only, y of y is function of y only, and z of z is function of z only. And therefore, differentiate equation 2 with respect to x, y, and z twicely. And therefore, First we differentiate with respect to x. Dabba psi by dabba x equal to y and z constant yz dabba x by dabba x, and therefore dabba square psi by dabba x square is equal to yz dabba square x by dabba x square. Similarly, differentiate with respect to y, equation 2, we get dabba psi by dabba y, at this time xz constant, xz dabba y by dabba y, dabba square psi by dabba y square equal to xz dabba square y by dabba y square, and also differentiate with respect to z, equation 2, twicely we get dabba psi by dabba z, at this time x and y constant, dabba psi by dabba z is equal to xy dabba z by dabba z, and therefore dabba square psi by dabba z square is equal to xy dabba square z by dabba z square. Substituting this equation in equation 1, we get किमती पुट केलं त्या ठिकाणी yz dabba square x by dabba x square plus xz dabba square y by dabba y square plus xy dabba square z by dabba z square plus k square साईची किंमत टाकली त्या ठिकाणी xyz equal to 0. Dividing above equation throughout by xyz, we get 1 upon x dabba square x by dabba x square plus 1 upon y dabba square y by dabba y square plus 1 upon z dabba square z by dabba z square plus k square is equal to 0. And 1 upon x, this dabba square x by dabba x square equal to minus sign in bracket, तिथं पूर्ण टर्म पुढे येतील 1 upon y dabba square y by dabba y square plus 1 upon z dabba square z by dabba z square plus k square. You know the equation 4. And therefore LHS of equation 4 depends only on x, while RHS is depends only on y and z. Equation 4 is true only if each side is equated to constant, say minus m square, and therefore 1 upon x d square x by dx square equal to minus m square. These are ordinary differential equations, and therefore d square x by dx square plus m square x equal to 0. Denote the capital A. Similarly, right hand side equation can be written as minus in bracket 1 upon y dabba square y by dabba y square plus 1 upon z dabba square z by dabba z square plus k square bracket complete equal to minus m square. Both side becomes negative, then it becomes the positive, and therefore 1 upon y d square y by dy square equal to minus 1 upon z d square z by dz square minus k square plus m square. Note the equation 5. This can be written is in the form of ordinary differential equations. The LHS of this equation depends on y only, while RHS depends on z only. And here the above equation is true only if each side is equated to constant, say minus n square is another constant, and therefore 1 upon y d square y by dy square equal to minus n square. Yes, d square y by dy square equal to minus n square y, d square y by dy square plus n square y equal to 0. Note the B. And minus 1 upon z dabba square z by dabba z square minus k square plus m square equal to minus n square. Change the sign. 1 upon z dabba square z by dabba z square plus k square minus m square minus n square equal to 0. The k square m square n square is the say constant term, and it is also another constant, say p square. Now let k square minus m square minus n square equal to p square. Since k, m, n are constant, and hence p is also constant, and therefore this equation can be written as, in the ordinary differential equation form, 1 upon z d square z by dz square plus p square is equal to 0, or d square z by dz square plus p equal to 0 due to c. And thus Helmholtz equation in Cartesian coordinates can be separated into following three ordinary differential equations, that is d square x by dx square plus m square x equal to 0, d square y by dy square plus n square y is equal to 0, and d square z by dz square plus p square z is equal to 0.